Hello everyone and welcome to SYTA 2021. Myself Ankur Chauhan. I'm a senior tunnel engineer at SMEC India, and this presentation is jointly prepared by myself and my colleague Mr. Harsh Sharma, and it is regarding the probabilistic analysis for design of underground structures, focusing on the numerical approach. So to begin with the introduction of the probabilistic approach, which is used where the input data, that is the geological and geotechnical features, has various uncertainties, and these are represented by using their mean values and standard deviation values. So basically where we do not have any uh, well-known values of the input parameters, there we can use the range of the values for the input data, and that data can be checked in order to see the sensitivity of various parameters. So basically these data follow a typical Gaussian distribution like a normal distribution or log normal distribution, which you can see here on the screen, like a normal distribution curve showing the distribution of various input parameters. So this approach has a reason to be used, and it is used because the numerical modeling is generally carried out using a deterministic approach where the rock mass parameters are generally known in advance as a result of the geotechnical investigations. And if in case there are some lack of data or information where we do not have much idea about the definite data and information of the rock mass properties, so there we can very well use this approach in order to accommodate the variability in the properties, and that's where this approach has a major benefit in design, and it basically provides a better understanding of geomechanical properties, and it also accommodates the project risks and is more reliable and gives the more reliable estimation of the cost, because it gives us the best and the worst case scenarios, and it also gives us a better vision on the spectrum of uncertainties. So out of the probabilistic approaches, we have few very commonly used approaches, namely the point estimate method, which is a very commonly used method, but it generally uses the extremes of the range of input parameters. As you can see here in the curves shown, that the solution is represented as a function of the input parameters taken here as x1 and x2, and as a solution computing the estimation points, it calculates out of the various combinations in order to derive the most suitable solution, which is accommodating the all the extremes, that is the worst case scenarios to be encountered in the problem, and the solution is coming out as the most conservative one, as we can say. The next most commonly and I would say most simplistic approach followed here in the probabilistic analysis is the Monte Carlo simulation, which is one of the most popular method, and is an extremely simple in implementation, and works on its own algorithm, which starts with generating a random number from the assigned probability density of each of the predefined random variables. That is, for example, we can assign a certain range of values to any variable, like for example the Young's modulus or the angle of internal friction or any other randomly changing variable or the input parameter. And we can see the sensitivity of those variables on the results that we get out of the analysis, and it relies on repeated random sampling to address the risk and uncertainty in quantitative analysis. So basically Monte Carlo simulations has been applied in several geotechnical engineering problems because of its simple nature and easy to implement nature of the approach. So here we have taken a case study of a highway tunnel which is having a width of 14.5 meters and a height of 13.5 meters and having a highest overburden of 400 meters. So here we have assumed hydrostatic conditions having the in situ stress ratio as 1, and we have, for the variables, we have taken the three main very important parameters like elastic modulus, cohesion, and friction angles. All other parameters are kept constant for this analysis. And for the support, we have modeled 10-meter long 32 dia bolts at a spacing of 1.5 meters center to center. And you can see a typical sketch of a model that is being simulated. So for the input parameters, we have some general characteristics shown here, like the unit weight taken as 27 kilonewton per meter cube, and the ranges of the elastic modulus varies from 4 to 8 GPa. For the cohesion, it varies from 0.6 to 1.4 MPa, and for the angle of internal friction, it varies from 25 to 30 degrees. Few other constants are the Poisson's ratio is taken as 0.25 and tensile strength as 66 kPa in this case. So the design procedure, it is used with the Monte Carlo approach, which is having a sample size of 20, and the relative minimum and maximum values are corresponding to 3 times the standard deviation, and distribution are considered as the normal distribution curve. And you can see here the model is being simulated using the normal distribution, and the mean and standard deviation and relative minimum and maximum using the range are being shown here. The yielded element combination which are shown on the screen, you can see that in case of the extreme cases where we can see the combination of all the cases showing that the on the right hand side you can see the mean value case, which takes the mean values out of the most recurring variables or the most recurring outputs. So if we compare both the cases, we can see that if we take all the extremes of the results, then definitely our recommended support is not good enough looking at the yielded elements. And if we see the mean value cases, then we can say that our suggested supports are just okay and can be used. So this the total displacement plots visible on the screen. It shows the mean value case, which is having a roof deformation ranges from 19.2 to 65.5, and the wall deformation ranges ranging from 23 to 65.5 mm. So the sensitivity approach which is a major benefit out of carrying out the probabilistic analysis. It shows the different analysis has been carried out for the parametric study. That is, we vary the different input parameters in order to see its effect or the sensitivity on the result, in order to see that which input parameter has a major impact on the result. So it basically tells us about the criticality of a particular input parameter. So out of the several input parameters, we have taken some, basically three variables, like elastic modulus, cohesion, and friction angle. And output parameters are mainly displacements and yielding zones. And those are being analyzed to understand the behavior of surrounding rock near excavation. So as you can see, the effect on the yielding zone by varying all the three variables at a time, one at a time. Like on the leftmost image can be seen as the variation of elastic modulus only, which is showing maximum yield zone of around 7 meters. And the case of changing the friction angle shows the yielding zone of around 9 meters. And the cohesion variables shows the yield zone of around 11 meters. So it basically gives us uh, a tentative idea that the cohesion is having a major impact on the yielding zone, which is why the length of the bolt shall be defined critically from cohesion point of view in order to accommodate all the risk to be encountered. So just to review it from case to case, for firstly, the elastic modulus is used as a variable which shows the maximum displacement of 58.7 mm, and the minimum is 41.4 mm. So the total displacement value is found in the range of 12.5 to 58.7 by taking only elastic modulus as variable. So changing the friction angle will give us a maximum total displacement of 46.7 and 41.2 mm as the mean as the and the extreme cases. And so the range for this is 26.5 to 46.7, which is also a considerable range. And finally, the cohesion, which is varying, will show a maximum displacement of 56.1 mm for the extreme cases, incorporating all the different scenarios, to the 42.9 mm with the mean case. And it shows that the total displacement magnitude is in the range of 16.5 to 56.1 by taking the cohesion as a variable. So to conclude or summarize, we can see that deformation ranges are varying by changing different input parameters, and the variation are somewhere more and somewhere less, which gives us the sensitivity of that particular parameter towards the results. But in order to accommodate the risk, we have to check the sensitivity of all the parameters if we are not so sure about the particular values. So like every other system, this one also has some pros and cons. Like, the rock mass is not homogeneous, as you all know. So this approach captures the real picture of anisotropy, which is a good thing, and gives us a broader view of the rock mass, and it gives a better design life estimation of the structure with optimum supports and it also directly optimizes the cost of projects by comparing the variabilities out of different cases. And in order to further refine it and make it more holistic, or use it like a thumb rule, we can vary the different parameters or different behaviors or different failure of mechanisms in order to make it more reliable or make it more refined. And for the Monte Carlo simulation which is used, as the computational time increases, so it is limited to most complex geometry with many input variables. So although it is simple, but it is still more suited for the complex problem, because we generally consume a lot of time in order to compute these problems, and this kind of simulation is more suited in such cases. And the very basic problem in order to use this approach would be the projects which are in a very initial stage, where we do not have much of the information about the geology or any other geotechnical information. There we can very well establish some correlations and obtain some very useful results by varying the input parameters, which we can assume on the basis of engineering assessment based on the nearby projects or any minimum information that is available out of the tender documents or any minimum investigation that is being carried out at the project site. So this is very useful in those cases where we do not have much data. So there we can also check the sensitivity of the input parameters on the results. So this is basically about the very basic on the method of probabilistic approach. That's all from our end, and I'll be more than happy to answer any queries from your end. And once again, thank you very much for joining us on SYTA 2021, and all the best to all of you. Thank you.